All right. So we have already seen how the CPU fetches instruction, like grabbing the next line from its to-do list. But now comes the part where CPU actually thinks. And this stage is called as decode stage. The moment when the CPU stops and says, what exactly did I fetch and what should I do next? Think of it like reading a message. First, you look at the words. That means you fetch. Then you understand what they mean. And that's what you decoded. And finally, you act upon them. That's what execute is. So today, we'll step into CPU's brain right at the point where it is trying to make sense of what it just read. Let's begin this journey with a simple C program. So what I'm doing here, I'm writing a C program where I exactly am considering just say three variables into it. So let us say include stdio.h int main. Then we are having int a equal to 5, int b equal to 3. Then we are having int c, and just we'll write c equal to a plus b. And as usual, we'll try to print this result. Result is %d slash n double quotes comma c and then return 0. So like if we see this code, there's a little line c equal to a plus b. Seems very small to us, but to the CPU, it's a short story written in machine language. So we'll see that what exactly is shown there, but our understanding here for this statement is like this. So we are assuming that I'm considering a 32-bit instruction. So I'm moving value of A to EX. Then I'm moving value of B to EBX. And then I'm just saying add EX comma EBX. So sum would be stored with EX. And then I'm storing result with C. This is our understanding. These are not the exact instruction that would be used internally by the compiler. Okay, but this is our just understanding. So as I stated here, so what we are assuming here, move value of A to EX, move value of B to EBX, add EX and EBX values and store. Okay, so it is the last thing. Store the addition, or you say result of addition result to C. Okay, this is what. Now these four lines rather, if we see, are what the CPU will fetch, decode and execute step by step. Now let us talk about decode stage. Let us say once the first instruction, for example, move EX comma A is fetched. Though this would not be the exact instruction that would be added there, but it sits into a special place as we know called as current instruction register, IR. Now the CPU begins to decode it. Think of this as a CPU reading a line in a recipe. It says move. Okay, so I need to transfer something. So it asks a question, who is involved? So it says, okay, EAX, that's one of my registers. And where from? Oh, so it's a memory location represented by a variable A. And that's the CPU's moment of understanding the decode stage in action. So what actually happens inside during the decoding? So first of all, it has to understand and identify the opcode. The CPU, like when this gets translated into machine code, looks at first few bits are white. That's the opcode. The verb of the sentence. Currently, it is move, M-O-V. In our instruction, as we have, MOV is a verb which is representing move operation. Then next is operand identification. The CPU checks who is involved, the operands. So one operand is EX, that is register. The other operand is memory. Okay, so actually, though we wrote here is A as A, just it would not be written as A, but it would be written something like this because it would be like a value. Correct. So it would be going like this. Fine. The other operand, like what we said, which is a memory location, which is holding value for A. Now, what happens is from this instruction, the CPU looks at few extra bits that communicate how to access these operands. So this is generally referred as addressing mode. So is it register addressing, memory addressing, immediate data, or so on. In this case, we are identifying that is a register to memory. Finally, what happens is control unit prepare signals to guide the next stage. Signals that will tell the CPU which buses to open, which registers to read, and where to send the data. And by this time, the CPU hasn't moved a single piece of data yet. It knows exactly what it needs to do next. And that's the beauty of decode stage. It's all about understanding and planning. Now let's go through each instruction one by one. So let me save this code, and with that, we will assume that there is no error, hopefully, and we'll compile this. So as I stated earlier, like even the way that I wrote, the code would not be seen that way because all the variables that I took are local variables. So they would be sitting into the stack. How it goes into stack, let us not much worry about this. Let us have faith listening to this that all local variables would be stored on the stack. So if I try to open the code, the assembly code which is generated here, you can see the thing that I was talking about, the values that we took for our code, okay, for as an immediate data are 5 and 3. So if we go below and see somewhere, these are your two local variables. So this is like when we say 5 value, we moved that 5 into A, and this A is represented as memory here. This is B, which is holding 3 value. And then those values are moved, and then addition is done here with ECX and EDX. These values are moved into the stack, okay, or the base pointer at different as a local variables. Then those would be fetched into registers respectively, and sum is done. And then this would be your C, EBP minus 12 would be your third variable C, which is holding the result. Correct. Now, if we see, like say for example, 1, 2, 3, 4, 5, 6. These lines actually are what the CPU will fetch, decode, and execute step by step. Though in the earlier, what are the code that I showed you, I wrote it as 4. But actually, at the time of real translation, it would be taking more than 4. Now, if we see this particular instruction, say, okay, let us compile this and generate an executable. So if I execute this code, it would be showing me result is 8. But let us try to do this debug. Now we know that A would be having value 5, B would be having value 3, and so on. But it would not be directly seen over here because we are seeing through the C code. If I could have written it as an assembly code, then it could have been very easily understood. But our goal is not to really talk about right now whether to use C or assembly. Just we are trying to understand what exactly this decode stage is. So once the first instruction move ex comma a is fetched, it sits into special place called the instruction register. So let me try to execute this. So we'll display instruction register, that is our instruction pointer. Okay, this will hold the address of next line to be executed. Now let us execute the code and we'll print values. Now print value A, value B. There is nothing. Correct. Let us say step. If I try to print A, now you can see it actually executed move A equal to 5. That means definitely internally it would be different. Now one can see here, like while it was executing this line, address of it was this main plus 28. Then this was the next line, integer b equal to 3. That's where it got instructions. And we saw there are multiple instructions involved there ultimately inside the code. And this is what your instruction register is containing. Now think of this as a CPU reading a line in a recipe, like it is reading one by one. You can see here, when I'm using a debugger, GDB, to demonstrate this part, it is not expected that you should know how to make use of GDB. Just here, what we have to understand is like to see how the program counter is, like in this case, it is instruction pointer is getting increased. Okay, depending on number of, because we are executing through a C code, that's why it would be difficult to see like whether it is increasing by one or what. But if you see B9, then it would be BA, BB, BC, BD, so on. Then it will reach to C0 when it goes to BF. Correct. So those many lines are internally taken care of. So like one would have seen here, like we got now those results. Now, because we are using C code, ultimately, it would be difficult for us to go through each line and so on. Now, to help you out on this front, okay, let us continue the execution. So let me write step. You can see C equal to A plus B. If I try to print A, print B, and print C. Now C doesn't have any value at least right now, though it is showing us 1. We don't know, that may be garbage. But when we say step and we try to print C, then you can see the result is stored with 8. Again, some operation internally happened, and this was done through the decode mechanism. So now if you see, how come this value of A, which was earlier shown like this, is replaced and we got 5? This was because it fetched that thing and then it decoded and actually executed. So execution also is taken care of. So opcode identification would be there. So how it would be shown? So let us try to check this out. So if I write say obj dump dash d a dot out, correct. Now if we go to say, if we write less, let us go to main code where we are having those values. Now you will understand here how exactly the instruction sizes differ. Okay, now let us see here. So say for example, this instruction requires 4 bytes, 1, 2, 3, 4. So 9D was the start, 9D, 9E, 9F, A0, and this A1, A1, A2, A3. Then this is A4, A4, A5, A6, then A7. So like this instruction requires 3 bytes. Okay, you can see here. This instruction also required 3 bytes. One can see here. This instruction required 4 bytes. And if you see here, this instruction require more than like these are 7 bytes. So they may vary, the instruction sizes may vary here. And if you see the first column here, actually, if I talk about this, say for example, which would be similar, yeah, move L. Let us take this move L. This operation, move is move operation. You can see that this C7 and C7, this actually is your opcode. 8B is opcode for move. 8B is opcode for move. Now it may vary depending upon what the types of operands are. And that's what I was referring to earlier as addressing modes. What kind of data is available as operand? Say, for example, here, one can say it is register to register. Here we are talking about memory to register. Correct? This would be like immediate to register. This is immediate value that is added. Correct? So here, like if I see, this is also immediate to register. So the sizes may vary depending upon what kind of operands you are having. Fine. And like depending upon the operand types, these opcodes may change. Okay. Now we have not too much worry about why these opcodes are changing rather right now. But we have to understand that these operation codes are changing to communicate exactly what operation is to be carried out. Now, when we said that this 5 should be assigned to as a local value, value for a local variable, it is doing that, and this 5 is stored in this way. 3 is stored in this way. Correct? And this notation is called as little Indian notation internally. So by this time, like when we say the CPU hasn't moved single piece of data yet because we are not executing, but it exactly knows what it needs to do next. And like if you see, like when it start execution, this would be like linking time binding. At runtime, address would be different. What we saw there with EIP, correct? Like this line would be having some different information or maybe opcode or sorry, not opcode exactly, but the address would be different. So this address is what your linking time address. After linking, the address is generated, and runtime address would be what we saw with EIP above. Now, when we see these all instructions will be varying according to the size, depending upon what values are passed. Now, let me make it simple. Let's see the fascinating world of assembly. Now, in x86, like Intel architecture 32 or Intel architecture 64 bits world, instructions are not all of same size. We saw here. They can be short, they can be long. Let us see with example. Like for example, the code that we wrote earlier. Let me write the similar code in assembly. Let us say fetch.asm. So I'm using Intel 32-bit instruction set. Just see the code. Let us not much worry about what is happening. We will not print the values, but we will try to just see the values. Section.text, which communicates that that is the code to be executed from this place. Now we have to communicate that code would be starting from main. Then you just say move ex comma 3. Oh, we had move ex comma 5. Move ebx comma 3. Add ex comma ebx. And if I want to store the value, okay, in variable, I will show you that part too. Okay, let us say we are not printing, but we will see this result, what happens there. Now, if you see, we have some addressing mode like immediate addressing mode is added here because we are providing immediate values, like values are served to their other plate. And this is as both the registers are involved. So this is register to register. So let us save this and let us compile. So let us assemble this first. NASM-ALF32 fetch dot. I'm using assembler. Don't worry, you can skip that. Just try to understand what exactly I'm trying to show you. So if you repeatedly see this video, you will understand what exactly I'm trying to communicate. So then I'm generating executable fetch.o dash g dash f. Let me use the GDB. Okay, now before that, let me show you how the code is generated after assembly. These are like if you see, these are the line numbers. This is compile time binding or a translation time binding. That's what we call. We haven't yet we haven't created what you can call it as an object code. Correct? This is before the object code. So you can see B8 is communicating me that there is a move instruction with EAX. BB is communicating me that there is EBX, move and EBX are involved. And 5 and 3 are the values. Then 01 D8 actually communicates that there is add, but that add is containing two registers EX and EBX. So if I do this same thing, say for example, if I make some changes in the data, in the code, like what is the code that we wrote? Let us say I'm repeating this. Let us take here 6. Let us take here 89. Okay, and let me change this to ECX and ADX. ECX and ADX. I change the registers. Now let us check the file. Now you will see like B8 is communicating that there is EX. BB is communicating that there is EBX. BA is communicating that there is EDX. B9 actually is communicating that there is ECX. And if you see, the 01 actually tells that there is addition. And this D8 is communicating that there are EX and EBX involved. This D1 is communicating that ECX and EDX is involved. Right? And this is what the decoding stages. It decodes this data. So if you see here, like the instruction sizes are involved there. Like in this case, like whenever we have immediate data with move, the size is 5. Instruction size is 5. When we add both the registers, then instruction size becomes 2. So the more information the instruction carries, like memory address or immediate values, the longer it becomes. So to do so, to understand that, let me show you one more thing rather. So here I am adding section dot data variable, say a global variable. I'm declaring that integer. So integer is declared like this. Okay, don't worry about what exactly is seen here. So now let us say if I am adding, changing this. Here I am taking now different registers, ESI and EDI. And here just I am saying that it should pick value of A and it should pick value of B. Fine. Now we would be adding ESI and EDI. Let us save. Let us assemble. You can see the code. See the changes. Now instruction size. We had memory involved, so it is displaying, showing that memory as an address, right, with the square bracket. And you can see now that move earlier had B8, B8, BA, B9. It is changed now to 8B. This is 8B. Correct. So somewhere there would be a change. Now if I see this add, each add that we added here was carrying 0, 1, 0, 1, 0, 1. But depending upon the operands that it is having, it is considering different values here. So this is what the decoding is. And operation, your CPU understands this part which is shown here, like which is highlighted here. Right? One can check this. Okay, this is the only part that machine understand. It doesn't understand what is move and so on. This is translated by your translator into what is machine understandable code. This is fetched and then decoded. What exactly this BA means, it decodes what operation is there. Correct. So like if let me now show you how it works. Let us compile, create an executable. Now when I said that first instruction would be, say we are starting from here. So if I write L, you can see the code. Your code is okay. Let us say run. Let us display the values. Now if you see, like we don't have anything added here yet, correct? So EAX equal to 5. If I display, your current next line of execution would be this 7. And this 7 is from the user's code. But if we try to see that part from machine code or machine way, so it would be this, which is represented like this. Correct? EIP, your program counter is containing that number. So when I say move EX comma 5, if I say next instruction, you can see that 5 got copied. So operation got carried out. Correct. This is execution that is happening along with it decoded, it got the operation, then it actually applied, and that is what the execution stage also is considered over here. Correct. Then now if I see for EBX, it is done. Now add EX comma EBX, you can see 8. Now let us display EDX2 and ECX. Let us see EDX we got 6, ECX we got 89, 95. Let us display ESI2, ESI and EDI. You can see first value was 10, second value was 40. You can check it here. So if I write L1, you should see your first value 10 and 40, and that's what are shown here. Right, and then next operation was add thing. Correct. So return rather. So this is how it works, and this is what the decoding stage is. So let's recap. What we saw here, the decode stage comes right after the fetch. CPU splits the instruction into opcode and operands. It figures out the addressing mode, how to access the operands. It prepares control signals for the stage, and decoding is carried out depending upon what is the size of instruction. One can think of this stage as CPU's thinking time, and it's not doing any work, though we saw the execute stage too. But prior to that, like before execution, it should understand what to do, and that's what the thing is. And when we saw exactly the values moved, that's what your execute stage is, where the CPU puts its plan into action, right? And this is how you can understand the decode and execute cycle. Thank you.